devoted to generalization to one of the classical image processing methods, blob detection. In our paper, it is generalized for a general setting of an image being a map between manifolds. So, as if usually a grayscale image is modeled as a function from R to R, this generalized image is modeled as a map between two finite-dimension linear manifolds. So the problem is to propose blob detection method for a map between manifolds. The main points of our solution are the following. First, so the main points of our solution are the following. The first is to consider an image graph as a submanifold. The second is to define blob response functions through by means of image graph curvatures. So let's go into more detail. Firstly, I will introduce you to blob detection. So it is a widely used image processing and computer vision method. It has application in many fields of applied mathematics, image processing. Informally speaking, it aims to find ellipse-like regions of different sizes with similar intensity inside on the grayscale images. And, blobs are found as local extremums of a blob response function. So, firstly, this method was proposed for grayscale images. Then it was generalized some years ago for an image being a real valued function on a two-dimensional manifold, and also there were several approaches to generalize to a vector valued function on Euclidean domain, but this approach doesn't suit for manifold valued functions. So let's go into more detail into blob detection method. So this algorithm can be divided into 3 steps. The first is to calculate a scale space. Oh, I forgot to mention that we are talking about, formally speaking, a grayscale image on surface. So there is a two-dimensional surface, and there is a real valued function on it. And, so I will tell about blob detection as it was proposed in previous works, which we want to generalize. So the first step is to calculate the scale space. It is calculated as the solution of the heat equation on the surface with initial image as initial conditions. Then calculate a blob response. So it can be determinant of scale space, or determinant of the Hessian of scale space, or the trace of the Hessian of the scale space. Then find blobs, centers, and scales through the calculated blob response function as local extremums of blob response functions. So let's then consider a general case. We now have a map between two manifolds, finite dimensional, smooth, Riemann. Let's look how can we generalize block detection, which was previously mentioned, for this general case. The first step, so now we have to solve a heat equation for a manifold valued function. So there are methods to solution of such equations, but they are out of scope of our paper. But there are methods to generalize this step. The second step, the calculation of block response. So we see that for the general case, the Hessian is not a matrix anymore, so we can't calculate its determinant. The third step, calculation of block centers. So we can calculate a trace for Hessian for the general setting, but it will be vector valued, so we can take it minimum or maximum. So we see that the problem, the main obstacle to generalize block detection for the general case is are block response functions. So the main question is how to define block response functions for the general case. The ideas of our solution are the following. The first idea is that if we consider the image graph as a submanifold immersed in the product of domain and codomain spaces, then the real valued, so grayscale and manifold valued cases, so the usual cases and the general case differ only by the co-dimension of the embedding. And, so we took the problem into another plane. And the second idea is to use the mean and the scalar curvatures as block response functions. So they are defined for all co-dimensions. They are scalar valued. They are close to the Hessian trace and determinant if tangent spaces to the image graph and to the domain manifold are close. So two obstacles, two problems: how to make tangent spaces of image graph and the domain manifold close. We can make such a thin transform that the metric of the graph is scaled by a number mu. If domain and codomain are Euclidean spaces, this looks just like in the picture, like the following. And so the second obstacle is that if the scalar curvature of domain manifold is not zero, so if it is a curved space, then the block response will depend on it, and we don't want it. We want it to depend only on our function, on the manifold, on the image. How to deal with it? We can use, we can call it a relative scalar curvature, so we can subtract from the scalar curvature of the manifold formed by geodesics. So obtained by exponential mapping from a tangent space of the graph of the image. So let's look now to the formal definition, to the formal representation of the previous ideas. So we propose the following expressions, the following definition for the blob response function. So as I said previously, the blob response function. So as I said previously, we make tangent spaces of domain manifold and image graph manifold closed by applying such affine transform. And the second idea, which I said, that we subtract the scalar curvature of exponential mapping from the tangent space of the graph function. Of course, such definitions are not easy, are difficult and inconvenient to work with, and furthermore, such definitions don't provide the connection to the original method. So, from these definitions, we don't see that the proposed method generalizes the original method for the case of real valued function on manifold. So in order to take this into account, we propose such theorem which connects our defined blob response functions with the Hessian. So firstly, it gives an easy way to implement and to calculate our blob response functions, and then gives the corollary that our proposed method coincides with the usual method for the cases for which usual method was defined. So this is all for the theoretical part. We'll not go into detail for the proof, just the main points of the proof. So the proof of representation of our blob response function from Hessian. Main points are two lemmas. The first connects the Hessian of a function with second fundamental form, and the second lemma just gives a representation of the second fundamental form through the Hessian. So those who are interested can look into the full proof in the article. So we also conducted some experiments. This method was tested for the problem of chemical compounds classification. It is also called the QSAR problem. So the task is to distinguish active and non-active chemical compounds using their structure, on the base of their structure. Each chemical compound is represented by triangulated molecular surfaces with physical, chemical, and geometrical properties defined on the surface. So input data can be modeled as a two-dimensional manifold with a vector-valued function on it. So the proposed method was a part of the procedure of constructing the descriptive vectors for the chemical compounds. So the part of the procedure of projecting each chemical compound as a vector. So the procedure is a usual procedure for computer vision, image processing, and related fields. So detect blobs by our method, form pairs of blobs on each surface, and then use a bag of words approach to transform these pairs of blobs into vectors, and then apply to the obtained vectors usual machine learning methods. Okay, I think I will not go into detail of implementation here. So we conducted experiments on 6 sets. We compared our two blob response function and also naive approach and method for color images adapted to this case also by us. So the difference is not very big. So here is the table. In the table, you can see the cross validation, the value of cross validation functional. This value was used as the value of quality of build classifier based on the descriptor. So this value can be viewed as a quality value for the build descriptors, and so the quality value for different methods of blob detection. And so the difference is not very big, but we can see that one blob response function, scalar blob response, gave the best results almost in all methods. So this approach can have practical application in this case and in our. So this is example of results of processing of a chemical compound. This is a triangulated molecular surface. As a by color is denoted the scalar blob response function. So here you can see the color bar, and by white dots. The found blobs are denoted. So here you can see the blobs of a fixed size. So this is only the center of the blobs. The size of the blobs isn't depicted here. The future work, the first interaction is to generalize our framework for a more general case, not for a map between two independent manifolds, but for non-trivial fiber bundles. In particular, such generalization will cover an important case of tangent vector fields, which is not covered by the current generalization. And the second direction, of course, is to apply the developed methods to more practical application, to more types of data, to test it and to see the results. So that's all for my talk. Thank you for the attention.
Remarks?
I'm not sure to have how the scale is handled. You detect a blob with a scale, or the scale is a parameter of the method? The radius, the blob is.
Yes, the blob is detected with the scale, so the blob is detected as the local extremum of the scale space along x and along t parameters. So the procedure of detection automatically gives the scale. So the t at which the blob was detected is the scale of the blob.
So,
If you speak in Somali, it's better
It's recorded.
It's not clear to me, is this limited to blobs of an elliptical shape? Or can you also, I don't know, by a mix of ellipses, something like that, characterize the shape of a blob, a more complex shape?
Thank you for the question. Finding elliptical region is not in the formulation of the method. It's like a heuristic understanding what it does. But in fact, it's just a key points detector based on second order derivatives. So the shape is not incorporated in this method.
One last question?
Sorry. How do you make the connection between the detection step and the classification step? You mentioned that you have a back or forward on what space?
Thank you for the question. So the connection is the following. We detect, on each compound we detect blobs by our method, then form pairs of these blobs also for each compound. So with these steps we have a set of compounds, and for each compound we have a pairs of blobs. And then according to the properties, at the previous steps I said that on each surface there are several physical, chemical and geometrical properties. So we use electrostatic potential, potential of Lennard-Jones, and curvatures. So we have 4 properties. By this, so we have pairs. In each pair we have 4 properties for each point and a distance. So then we, roughly speaking, make a histogram of it and decode each pair by a number. And then we count occurrence of each type of pair in each compound, and by this we get a vector for each compound.
One more question.
Just one last, in this compound application, why did you choose a two-dimensional manifold? Do you consider that it may be a 3D manifold, no?
Because I didn't choose it. This was just a task. So to classify chemical compounds on the base of their molecular surface. So there is a hypothesis that molecular surface is important in chemical biological interactions. So we used this.
The information only about the surface. Okay.
Yes, information. Yes, information. No, yes. This surface is two-dimensional. So because of this, we applied to the two-dimensional case and to vector valued function.
Thank you. Thank you again.